Oh, wow, we're behind. So a Wikipedia page explaining it all. Now, all of this was from 8 years ago or 7 years ago. But my point is that all of these were generated blindly by a very simple recurrent neural network with simple architectures. The code for it can be found, still be found on Andre Karpathy's GitHub page. Again, observe the date. This is May 2015. And we could already do this in 2015. So if ChatGPT should really not be shocking you, right? And the most, what should be shocking you is that you really already know how to train a network to do something of this kind. And we will see how, right? So all of this is an example of modeling language. You're modeling language using recurrent neural networks, or more generally, language models and embeddings. Now, what is a language model in the first place? If I speak of language models, what do you think of when I ask you for what a language model is? Yeah.
Something that predicts the next word or token.
Is that it? Anything more profound than that? Yeah.
Model like an entire sentence based on the context that was provided to it by
Anything better than that?
making a grammar language.
Or anything better than that? Yeah, you're all kind of on the correct, partially correct. But what is a language model? It's essentially a model for all of language, but from a statistical point of view, it is a probability distribution over all possible sentences in the language. How many word sequences do you have in a language? Infinite, right? So you're actually learning a probability distribution over an infinitely large support. Fundamentally, this is no different from learning the probability distribution for a dice. If I wanted to learn a probability distribution for a dice, what would I do? I would just keep rolling it and rolling it, count the outcomes, and count proportions. Can I do this with language? No. Okay. So why? Pardon me? If you thought of this as a dice, this is an infinitely sided dice, right? If you rolled it infinite times, the odds are you would still not see most of the faces. So you can't just use counting, which is why you need some kind of a model. Now, why do you need to have, what are the uses of knowing the probability distribution of some random variable? Why would you want to know it? What are the things you can do? No, but that's what language, right? I'm asking, why would you want to know the probability distribution of any random variable?
We can do the expectation.
You can do expectations, conditioning. You can compute the probability of any given outcome, right? If I know the probability distribution for a dice, I know what the probability of 6 is. So you are able to evaluate the probabilities of different outcomes. What else can you do? What can you do? Predict. What can you predict?
Based on the current time, predict the future based on like the transitions that we see.
So again, I'm speaking of a generic random variable, right?
Right. Yeah.
What can you do? Yes.
If you have half a sentence, you can predict.
Speaking of sentences, I'm asking of a generic random variable. So that's an estimation procedure. But what you can do with a random variable is to draw samples from it. Correct? If I can simulate stuff, I can generate stuff. So the two things you want to be able to do with the probability distribution is to know what the probability of a specific outcome is. And the second is it enables you to draw samples from the distribution. These are the two main things you need to be able to do. But there's more. You want to be able to compute expectations. You want to be, and if it's a discrete random variable, you want to be able to rank order outcomes, which is the most likely outcome, which is the second most likely outcome, which is the sixth most likely outcome, right? So these are all the things you'd like to do with a probability distribution over a discrete random variable. Can you do this for a language? Which of these can you do for a language? It's very hard, right? We really don't know. Why? Because the support is infinite. If I wanted you to go and tell me which is the most likely sentence in English, there's no way for you to sort of inspect a dice and say this face is the most likely, simply because it has infinite sides, right? If I ask you what is the expectation of something, an expectation requires you to sum over all possible outcomes. This random variable language has infinite possible outcomes. You cannot compute expectations. But the other two things you can possibly do. And this is compute the probability of any specific outcome. And secondly, sample from the distribution. And language modeling, as we will see it, is going to give you a model which permits these two actions. Compute the probability of a specific outcome, a sentence, and secondly, generate sentences from the distribution. The rest of it is not technically feasible, but you can approximate it, and you're going to need these approximations later, okay? So from our perspective, here's the question. Suppose I told you 4 score in 7 years, what is the next thing? A go. If you're American, you know this, right? If I said A, B, R, H, A, M, L, I, N, C, O, L, what is the next character? Why do you think so? Right? Why do you think so? Yes. I could have just chosen K, right? Doesn't matter. What stopped me from saying A, B, R, A, H, A, M, L, I, N, C, O, L, K? So what were you doing over here? What were you doing? Pardon me? You were giving me the most likely, in your opinion, you were giving me the most likely next word or the next character. What did you have in your head? You had a language model, right? You had a model in your head based on which you were making predictions. You picked the most likely outcome. We want to take what's in your head and put it in a neural network. So the mechanics of it, that making sense? It's not just about taking a string and predicting the next word. What you are really doing is learning a model for all of language. But then when I break it up in this manner, I'm doing something very simple. I'm actually making some assumptions. There's always chalk missing, right? There's one. And here is what we do. I'm always interested in something of this kind. P of W1, W2, W3, WK. This is an entire sentence. I'm interested in the probability of the entire sentence. This is what your language model is supposed to be doing. What I am going to do is to break it down and say this is P of W1, and this is the parameter for my language model. And then I'm going to say P of W2 given W1 semicolon theta, P of W3 given W1 and W2 semicolon theta. What does this look like? This is Bayes' rule, right? I can decompose it. What does this look like? Does this remind you of recurrent neural networks? What does a recurrent neural network do at any time? It's giving you P of Y given x1 through it's giving you P of yt given x1 through xt, correct? If you were going to be using a recurrent neural network to do this, what would you be doing?
Feeding the output as an input.
Because when I'm giving you P of W3 given W1 and W2, it means W1, I'm giving you the sequence of outputs as the input, and what am I predicting? The next output. So this is the decomposition. This is what is called an autoregressive model. We've encountered these, the output goes back into the network. But at the end of the day, we are really trying to learn to model the probability distribution for the entire word sequence. That making sense? Right? So, but let's get into the mechanics of it. First, we want to represent the words in some manner for this to work. We're going to represent them as one-hot vectors. We know how to do this. If I have a vocabulary, I can represent them in some lexical order, and then every word is going to become a one-hot vector, which is all zeros with a 1 in the specific position of the word. And now if I break this down, so here's the thing. When I write it in this manner, then what I'm really doing is simply learning to predict the next word given the previous n words. Now, there are two ways of doing it. What were the two ways we saw of doing this? If I'm predicting yt given all x's, what were the two ways of doing it? You could actually look at a finite window of the past, or you could look at the infinite window of the past, right? You remember this? This was any kind of time series, right? So here, I could be just have my network. And this was the simplest one. This is giving me wk, and let's say this is w0, 1, 2, 3, 4, 5. And if I were trying to predict w6, I could be predicting w6 based on just w5. This is supposed to predict w5, so these two are the same, right? But let's ignore this for the moment. Or I could be basing this based on w5 and w4. Or I could be basing this based on w5, w4, and w3. This is, what kind of model is this? What kind of model was that? CNN. This was just a CNN, correct? You remember, right? Except that you're using the output sequence itself as the input, all past outputs as the input. So this would be the simplest way of doing a model of this kind, right? And so in that case, you're predicting Wn as a function of the finite set of previous history. So that's what your net function, the basic function itself is going to be. That is the basic function of a CNN in any case, right? And so if I were to draw a model, that's what it's going to look like. I'm going to say W0 through Wn minus 1. If I'm predicting the nth word based on the past window of words, W0 through Wn minus 1 are going to be presented as one hot vectors, and then the network must predict the next word. Everyone clear about what's going on here? Now, what is the problem with using one hot representations? Why do we use one hot representations? Anyone? Yeah.
They get very large, and it.
Yeah, but why do we use them? Yes, Denise.
Like, if we have one variable to represent what value it is, inherently we build like ordinality into it. And because each word is independent and categorical, we need to represent it as its own like individual variable.
That's correct. So the point, what is the different distance between any two one hot vectors?
1 bit.
Square root of 2, right? Because each component is each of them has a value 1 in one direction and 0 in everything else, and no two have the value 1 in the same direction. And so when you look at one hot vectors, the one hot vectors are always going to be at the corners, the specific corners of a hypercube where the 1, 0 plane intersects the hypercube, right? So those corners, those are the only ones that you're going to be using. What is the problem with using a representation of this kind, Josh?
It's going to get very, very large.
It's very sparse, right? What proportion of the space are these data using?
Like n.
They're actually using 0 volume. Now, this is something shocking, right? The problem is that your training data use exactly 0 volume of the space. A data point has 0 volume, right? That's one thing. So you can't speak in terms of volume. This is going to be true regardless of how much data you use. But you can think of density per unit area. And this is going to be very, very sparse, right? So there are two problems. Your data are the density is very low. And secondly, we didn't want to say that these two words are closer than these two words. We wanted to sort of hide that, not make assumptions. But then 1, 0, 0 is a valid word. Suppose I take 1 plus epsilon. Is that a valid word? Is it? 1 plus epsilon, where epsilon is vanishing. It's vanishingly small. So it's 1 plus epsilon 0, 0. Is that a valid word? No, it isn't, right? It's only these points and only these points. The rest of them make no sense. They carry no semantic interpretation whatsoever. So this representation has this, it's mathematically nice. It doesn't make any assumptions about the relative ordering of words. It gives you meaningless representations. And more importantly, it's very, very sparse. Now, some things cannot be fixed, but we can try to This makes no assumptions about the relationships between any words. The distance between every pair of words is the same. But because the density is very poor, we can try to project all of these data down into some lower dimensional space, some hyperplane. And if you project all of the data down, their words down, and if you choose the hyperplane just right, then each word now becomes, it's no longer a one-hot vector, but moreover, the distance between the words may actually begin to make sense. The vector that you can draw between any two words might actually be meaningful if you learn this hyperplane that you want to project it on properly. Now, how can you learn such a hyperplane? Right? So if properly learned, the distances between projected points could capture the semantic relationships between words. But how can you learn such a hyperplane? A projection is just a matrix, right? And a matrix operation is a linear layer. We know this. It's just like having a weights matrix. And so I could have this projection matrix P, which operates on every single word. And this it's the same projection matrix being applied to every single word. And now, yes?
How do you know what dimension to go down to?
We don't know what dimension you want to go down to. So that is a hyperparameter for your choice, right? For you to choose. But then if every word is projected down, and now you use the projected down variations of the words to make the predictions, you expect to be able to make better predictions. And of course, you can train the whole thing, including the projection matrix, by minimizing the loss in predicting the nth word. So, and the projection, of course, is just a linear layer. This entire thing is now a convolutional neural network, right? Except that those projection matrices represent local layers, which are all identical. This is a shared parameter, CNN. And the shared parameter is this weight matrix W, which is what generates the lower layer, lower dimensional representation. Now, and so here's what our convolutional network is going to do. Every word is going to be projected down, and then you're going to use the past k words to predict the next word. In this example, I think we're using the past 4 words to predict the 5th word. Technically, this is an n-gram, 5-gram language model, right? You're predicting the past 4, using the past 4 words to predict the 5th word. Is this using all of past history? No, it's only using a short window because it's a finite response system. Nonetheless, it's conditioning every word. So on the past words, and so in here, there is an implicit assumption in that while this decomposition remains valid, you're assuming that the probability of any word is dependent only on the past 4 words. It doesn't depend on words way back in the past. Is this always true? Can you give me an example where we just saw this assumption being violated just a few minutes ago? The code, right? If a parenthesis is open, a curly brace is opened, you have to remember that it has been opened, and the possibility of closing it remains until the curly brace is closed, regardless of however long it takes. But once it's closed, it's no longer, you cannot be closing the brace again, right? So this assumption is not valid in most cases, but it's an assumption you could make. And when it comes down to engineering, there were a bunch of other solutions that people have used just to say, let me try to predict individual words. So you can try to predict a word based on words on both sides. Or you can try to use a word to predict words on both sides. These are also different variants. And all of these were originally trained to solve the problem of how do you project a word down to a lower dimensional representation. A great many solutions, soft bag of words, skipgrams, the straight up language model, CNN. And regardless of how you do it, it turns out this business of projecting words down to a lower dimensional representation ends up actually learning meaningful relationships. You're all familiar with this example. If you haven't seen it, the original paper on this by Mikulov et al. Had some very nice visualizations. They found that when they projected these words down, if you, for example, projected the words Beijing and China down, the vector from China to Beijing represents the relationship is capital F. And so you could add the same vector to Germany and you'd get Berlin. Or you could add the same vector to Poland and you get Warsaw, pretty much. So it ended up showing that these relationships. the projected down words actually captured semantic relationships. So you found, for example, that king plus woman minus man ended up giving you queen. Yeah.
As far as words are concerned, we can still try to estimate how many words should be considered, like 4 or 5. But as far as time series data is concerned,
So we are not going to be using this. This is a very simple model, right? But anyway. Time's up, guys. So can someone on Zoom tell me if the first statement is true?
Yes.
Second one.
Yes. Yes.
Something very active going on up there, right? So what were they trying to tell me about the remaining sentences? Is the third one true?
Yes.
And the
Yes.
fourth? Yeah. Okay, so
Yes.
the fourth is not true, right? Anyway, the distance between any two non-identical one-hot vectors is the same. Words are represented as one-hot embeddings because they do not impose any a priori assumption about which words are closer to others. Word embeddings derived from language models. So these projected down representations of words are what we call word embeddings. And these are lower dimensional, real valued representations where the distance between words is a meaningful representation of their closeness. And this has absolutely no way of giving you the representation of a word that's not in your vocabulary. If I'm using an if I am using an n-dimensional dictionary, n-word dictionary, I'm going to use n-dimensional one-hot representations to represent the words. If I want to include the n+1th word in my dictionary, I'm screwed. I'd have to add an entire new component to my words, and that is going to, my projection matrix does not account for it, right? Yes.
In the capitals example that you give, like the Warsaw, Poland or thing, like, can't you, if let's say Warsaw is not in your vocabulary, can you not predict that Warsaw will be close to
You can find out what the embedding is, but what is the corresponding word? You can't go back, right? So anyway, so let's go back. How can I actually incorporate infinite history? We know how to do this now, right? We've already done this in class. Yes, Advait.
Just on that point, so from an embedding, there's no way to import to get back.
Yeah, because it's a dimensionality reducing projector transform, right? Can you invert that? Can you invert a 3x1 matrix? Yeah.
So in all these models as well, the outputs will be one hot.
The outputs are one hot. The input is projected down. So look at the picture. I'm putting a P at the input, but there's no P at the output, right? So anyway, going from a finite response system, if I want to consider the infinite past, I just have to use simple recursion. I'm still trying to model this. I'm still trying to use this Bayesian decomposition, except this term, P of Wk, given W1 through Wk minus 1, semicolon theta. This is a recurrent neural network, which is using all the past words as input, right? And now, how could I use this? So we see how we are decomposing the probability of the word, right? How can I compute the probability of any word sequence now? So let's say I've trained the model. How would I compute the probability of any word sequence? Anyone? Yeah.
You could take the outputs, like W2 through 10 in this case, and then, do forward backward algorithm on the.
Where's the forward backward? Why do I need the forward backward? How do I compute the probability of any word sequence? So here is the thing, right? Keep this formula in mind. Now, I don't want you to get lost. Keep this Bayesian formula in mind. And now, suppose I have my network, whatever, and W0 goes in. What comes out? Does a word come out? What comes out? A probability distribution for the first word in the sentence. So what is going to come out is P of PW1 of W given W0, right? The probability for all the values that W1 can take. Correct? And suppose I feed W1 over here. What comes out over here? So this is going to be a probability distribution over all the words. This is also going to be a probability distribution over all the words, correct? And so if I pick the entry corresponding to W1 over here, it will tell me what the probability of the first word was given the 0th word, right? If I pick the entry corresponding to W2 over here, it's going to tell me what the probability of the second word was given the first and the 0th and the first word. So I can just feed all the inputs in, read off the probabilities from the table outside at the output, and the product of all of those probabilities is going to be the probability of the entire sequence. That making sense? Thomas? Anybody? So if I asked you to write code to, given a model, to compute the probability for any given word sequence, could you do it? Aishwarya? That makes sense.
Yeah, but like if we are calculating P of W1 given W0, like how is that a probability distribution for all the?
When I give it W0, it's actually generating a probability distribution over all the words in my vocabulary, is it not? What do you have at the output layer? Softmax?
Yeah.
What does the softmax give you?
Yeah, for all the words.
It gives you a probability distribution over all the words, right? Then I can just pick out the entry corresponding to W1, and that's the probability for W1, right? I can feed that in as W2. It's going to give, the softmax is going to give me a probability distribution over all the words. I can pick out the, the probability for W2, and so on. That making sense to everybody? Yeah.
Can you formally write out the equation in terms of how the calculated, how it like progresses through the chain?
Can you speak up, please? I can't hear you.
Can you write out the equation as to like how the probabilities like multiply together?
Okay, so that's easy. Let me. This is good. This term. And this is kind of. Come on, don't fly off. So the first, this guy here, this output is going to be for. This is the probability distribution for the first word, correct? And this is going to, and it's W given W0 semicolon theta. I'm just using this notation where this is the variable and this is the value. It's like saying P of X takes the value 1, P of X takes the value 2. Anyway, so over here, this is an entire probability distribution over all the words right here. That making sense? Saurabh? Okay, so if I want to find out what the probability of this particular word is, I just have to go and read that entry out of this table, correct? And just all I would do is multiply this probability and this probability and this probability and just chain them up, right? Because each of them is the probability of that word given the entire history which has actually been fed in. Making sense to everybody? Okay. So this is easy. Now, how can I use this to generate new sentences? So we saw that there were two things we wanted the probability distribution to be able to do. How to compute the probability of a word sequence given the word sequence. And the second is how do you generate a word sequence, which is how to sample from the distribution, correct? How can I do the second thing? So here's what I can do. I can feed in W0, right? I get a probability distribution for the first word. I can randomly sample from it. That's going to give me W1. I can feed that W1 back in. I'm going to get a probability distribution over words again. I can randomly sample from it. That's going to give me W2. And so I can, at each time, it's going to give me a probability distribution for the latest word given all the previous words until then. I can sample from it, and that's going to be my latest word. And that one goes back in at the next time, because now I have already determined this is the word, right? I'm going to get a new probability distribution. From that, I can sample the next word. I can keep doing this and generate my word sequence. Is that clear? Yes.
Isn't that too dependent on our prediction of W1?
Pardon me?
Isn't that too dependent on our prediction of W1?
It is, isn't it? But it's a random sampling. Is it an invalid sample? This exactly follows the probability model that we have, right? Using Bayes' rule, this is an exact draw from the original probability distribution, provided the neural network accurately computes the probabilities of words given the history.
What if we like went through all combinations?
Meaning?
Like we will see what the final result is after seeing all the combinations.
What is the sum? I'm sampling.
Final probability.
I'm sampling over here, right? So when for example, if I'm rolling a dice, do you have to worry about what comes out at the end? Sampling is the process of rolling the dice, right? So you're rolling the dice for the first word. Now, given the first word, you got a dice for the second word. You're rolling that. You're getting the dice for the third word, and you keep sampling, right? Yeah.
Like if like W4 is incorrect, then what are the rest?
There's no. This is sampling. When you roll a dice, where's the notion of incorrect? Right. I'm speaking of drawing a sample from the distribution. Yes.
You said if we assume that our model is modeling probability exactly, but wouldn't this magnifier like
So you can expect things to kind of average out, but yes, your model is not going to be exact. The more accurate the model is, the better, the better your sampling is going to be. Yes.
Two questions. The first, is there a reason that the output of W2
Here I've just took you. Assume that I've given you the first 3 words in the sequence, and you're generating the rest of the sequence.
Okay, and then my next question is, when you're tossing in the next word, why is it that you can disregard, like, if you're just randomly sampling the word, isn't the word that you choose heavily, like, doesn't that heavily impact the sequence of words that you get out?
But you're sampling the entire word sequence, right? I'm sampling. So think again. I want you to think back and realize that I have a probability distribution over all the words in the language, right? So when I'm when I'm sampling this distribution, what am I doing? It's like rolling an infinite-sided dice, but then I could equally well just do it word by word, which is basically what I'm doing. I'm randomly choosing the first word, then based on that, I'm randomly choosing the second word, then based on the first 2 words, and I'm randomly choosing the third word. That's it. So W4 is part of the sampling process.
Are you doing that from the distribution or just?
The distribution is the probability generated by the network, right? Yeah.
So usually when you take in terms of like the context that the first 3 words are providing to the rest of the probability, won't the probability of 1 and 2 also impact 4?
This is conditioned, given 1, 2, 3, right?
Given 1, 2, 3, but won't the first 2 words also play a role in
Yeah, that it is conditioning. If I give you at any point, everything in the past is conditioning the future, is it not?
And say this is to predict a sentence, and you have like say a period so that it's a sentence termination. So then is this model also capable of stopping prediction whenever you want and restart the prediction without considering the probability?
Okay, let's get back to that. Okay, so let me continue, right? So to answer your question, here again was our Linux code. And this code was literally generated using this process. The first thing that you fed in, W1 was an open brace. You generated it computed a probability distribution. You sampled a character from it. Then you fed that back in, and then it gave you a new probability distribution. You sample the next word, and so on. And when you did that, eventually you actually got this entire program. When did we stop generating stuff? Over here. When the final parenthesis was closed. Now you know the program is over, right? In some cases, you actually have a natural ending to things. I would like to play this bit of music. Someone actually trained a recurrent neural network, a very simple one, on MIDIs. And then you can generate music with using that recurrent neural network. It's perfectly decent sounding music. But anyways, so the point is that in many cases, I can keep doing this. We never know when to stop. And so a sequence of words by itself doesn't tell you if the thing is complete or not. Yes?
So in the example that you gave where the starting character was an opening brace, so if like for different code pieces, the starting character would always be the opening brace. So doesn't it become deterministic?
Meaning?
Uh,
It's a probability distribution. You're sampling from it. Sampling is never deterministic.
Oh, you still keep sampling, so there are chances that you'll get something.
You will get something different each time, right? It's only the first character that's deterministically given to you, right? So, making sense? Yeah, I've got to make sure that. Now, when do we stop? This is the key problem. A sequence of words by itself doesn't indicate if it's a complete sentence or not. So if I just told you 4 score and 8, is this a complete sentence? If it's not, is it the initial portion of a sentence? Or is it the final portion of a sentence, or is it in the middle? Just the sequence of words by itself doesn't tell you this. I mean, there's nothing stopping me from going on stage, saying 4 score and 8 and going home. So it could be a valid sentence, right? It's except that in that case, you need specific indication that this was it. So we're going to introduce 2 special symbols, the start of sequence symbol and the end of sequence symbol. And the start of sequence symbol indicates explicitly that the next word is the first word in the sequence. The end of sequence symbol indicates that the sequence has ended, that's it, go home. So if I just say 4 score and 8, it's neither the start of a sentence without these 2 tags, then it clearly indicates by the sheer absence of these 2 tags that it's somewhere in the middle of the sentence. On the other hand, if I say SOS 4 score and 8, then this tells me that those 4 words were the first 4 words in whatever sentence was being written or recorded. If I say 4 score and 8 EOS, then it tells me that these were the last 4 words of the sentence. And if I have an SOS and an EOS on either side, this was the entire sentence. This was all I typed, and that was it. So this is making sense, right? How these tags are important. If you didn't have these tags, and if I use my language model to generate, it's going to keep generating from here to kingdom come without stopping. You need a way of stopping, and you need a way of starting. So the question you should have asked me was, what was W1? How did I choose W1? W1 is always the start of sequence. I give it the start of sequence, then it begins generating. It stops when it generates, when you draw an end of sequence. Make sense to everybody? Right, so there's a put. I'm way behind time. Okay, guys, 5 seconds. All right, your time's up. Shichi, is the first one a complete one sentence? What about the rest? Is the second one a complete sentence? Anyone? Third? Fourth? Okay, because you need both tags, right? Only the first one is a complete sentence. So now let's return to our problem. That we spent a lot of time on language modeling and representing sequences. Our problem is to convert an input sequence to an output sequence. What we've already looked at so far is where the output sequence is shorter than the input and has an order correspondence to it. But this is the more interesting problem, where the output and the input may have no order correspondence at all. They may not even be related looking. For example, in I ate an apple, the output is longer than the input, and the words are mixed up. The German words are not in the same order as the English words. My screen is blank. Please check if your computer is plugged in. There's no word in the output that has anything to do with the input. So how do we actually conduct this kind of conversion? Do you mind shutting your laptop there? Thank you. So that problem is going to be handled using this model, this many-to-many model. The way we do it, you're going to have an initial portion of the network which consumes the entire input. And at the end, it's going to produce a single symbol. And this vector represents everything that the network has learned about the input. And clearly, it's possible to do such a thing because remember, when we were performing language modeling, when you are generating the 200th word, all the information about the history was in the hidden representation, which carried information about the previous 199 words. So we have reason to believe, and it seemed to do a good job, right? So we have reason to believe that this kind of representation can be effective. And then you have the second, so here's what the network pseudocode for it could look like. You just run through the input, and at each time, you're going to take the hidden representation at the previous time and the current input, and that's going to give me the hidden representation of the next time, right? And that's going to be fed back in. And now there's a second portion of the network which takes the hidden representation from the final instant and uses that as my initial hidden state in my recurrent generation model, and then it just goes ahead and recurses on it, and you can use that to generate word sequences. So here's what the code for that is going to look like. This would be the initial portion of the network, which just consumed the input and generated a final hidden state. And then at the output, you start off by saying that the hidden state for the output is the same as the final hidden state of the input. And then at each time, you're going to pass the last hidden state value in, and it's going to generate the next hidden state value, and it's going to generate a probability distribution over words, from which you would actually draw the word. So this, at each time, this is going to be a probability distribution from which you're generating the word. This is how it works. What would be the problem with something of this kind? There's something not quite right with this. What is that? Does the word, remember, at each time the actual word you output is drawn by random sampling, right? So, or through some drawing process. Does the word that you draw at the second time instant have any direct influence on the word that you draw at the third time instant? It does not, right? So for example, if you said that if you have drawn it was A in the first three words, or regardless of whether you've drawn it was A or it was an, because A and an are random draws, it doesn't change the probability of the word dark at the next time. So it could have, you could have just drawn it was A dark or it was an dark, and clearly one of these makes sense and the other does not, right? So how can you fix this problem? The fact that you chose the word A should increase the probability of dark at the next step, as opposed to what the probability you would compute for it if you had chosen the word an. So how would you fix that? So that's what you can take, right? You can have the recursion over the hidden state, but then you can also have the word go back in. And so here's what the simple translation, this is what I'm going to call the simple translation model. Here's what it's going to look like. You have the input is consumed. You get a final hidden state in the red box. Yeah.
So the sampling of the word was done based on the information that was passed from the hidden state. Right? So,
hidden state and the, yeah.
Yeah, so there's some information within the hidden state as well which is being passed.
Correct, but the point is the hidden, you might have got, for example, the probability of A and an being identical, right? Or very close. It's a random draw. There's nothing, you're not, so the point is, it should be influencing the future, it does not. Right? And so the input is on the input side, you're saying that the word sequence starts with an SOS and ends with an EOS. And when the EOS has finally been processed, you're going to get this red box. You know when the input is ended. Now you're going to go ahead and generate things on the output side. And so the hidden state at EOS stores all the information about the sentence. Subsequently, the second recurrent network is going to use this hidden activation as initial state. And the very first word on the output side is also going to be a startup sequence, SOS, right? So it's going to use SOS as an input initial symbol to generate a sequence of outputs. And this is going to keep generating outputs until you have finally got your end of state, right? So you might just have said, I ate an apple, then that hidden state along with the start of sequence symbol goes in, and you got some probability distribution from which maybe you drew the word A. That's going to go back in, and then you get another probability distribution from which you drew a word, and you keep going doing this until you actually pulled out an end of sequence marker. Right. So note that over here, if I had drawn a different word in the first position, because a different word would have gone in, the entire output would not be different. So it actually has the actual words you choose are actually influencing the output. Yeah.
What happens if your initial sentence that you use to generate the red box doesn't end in a EOS, so you don't know the SOS?
But it has to. Otherwise, it's not a complete sentence. You're going to keep processing the input until you have an EOS.
What I'm trying to say is, what if you run out of inputs midway through a sentence? You don't know necessarily the SOS.
So this is not going to work. You need to know when the word ended. If you decided this is the end of it, then you're going to have an EOS marker.
No, like for example, if you're only given I8N.
If you just gave it I8N, I'm going to assume that I8N is an entire sentence. So I'm going to stick an end of sentence marker at the end of it. That's all you gave me, so that is the end of the sentence, right? 4 score and.
What if you're trying to predict what comes next?
You haven't told me. How can I predict it? You haven't told me that you ate an apple. Why am I going to produce apples in German? Yeah.
Oh, okay.
Go ahead, Salome.
I'm sorry, can you go back to the it was O and it was an example?
Yeah.
Was not affected.
Look at this. If at the third word, I draw the word A, is the hidden state at the next time being influenced by the fact that you drew the word A?
So it is influenced only by the input at that.
There is no input. It's only being influenced by the hidden state, right, at this point. In this network, there are no inputs.
So when you say O and I see.
There is no input, is there? Right. Yeah.
Isn't like this inherently flawed in the sense that like it's a lot to pack into one hidden?
Thank you. We'll get to that later. Okay. So here's where we are, right? And I'm just drawing a network with a single hidden layer, but you can have any number of layers. This was just for illustration. And I have pseudocode for it. So here's what happens. At each time in the output, you're passing the last hidden state and the last word drawn to get the probability distribution of a word at the current time. And then you're going to be drawing the next word from that distribution, and that goes right back in. So there's a little bit of magic here. Drawing a different word at time t will change the next output because y out is being fed back in, right? Terminology, the portion of the network that processes the input is going to be called the encoder, and the portion that generates the output is going to be called the decoder. The encoder is encoding the input into this vector in the red box, and the decoder is decoding that red box vector into the output. Now, in practice, we're actually not going to be passing in one-hot representations. We're actually going to be passing in the down projected embeddings, because otherwise you're going to have too many parameters to learn. And the embeddings might be separately learned. The embedding matrix P might be separately learned. If you're translating from English to German, then obviously you're going to use different embeddings, different vocabularies on the encoder and decoder side, and they would have different embedding matrices. On the other hand, if you're doing a dialogue system, going from English to English, they would all be the same, right? Now, what does the network actually produce? At each time, remember, the network is producing a probability distribution given everything that came until this point, right? So over here, it's computing the probability distribution for the first word, given the entire input and start of sequence marker. At the next word, and this drawn word is being fed at the next time. So now at this time, it's going to be generating a probability distribution over the second output word, given the entire input and the first two words of the output, right? So basically what we are doing is exactly the same as this. We are actually computing now P of SOS, given the input is basically 1, so you don't have to worry about it. The first word has to be the start of sequence marker. But then the next thing is going to be P of word 1 at the output, given SOS and the input. The next one is P of W2, given SOS and W1 and the input, and so on, right? At each time, it's computing the probability of the latest word given the entire input and the portion of the output generated so far. So what is this process of drawing doing at each time? The drawing is trying to draw a sample from the distribution for the next word, given the entire inputs and all the words that have been drawn until now. And so this magic operation is basically just a sum drawing operation. You can have different drawing operations. You could pick the most likely, or you can pick a random word. Yeah.
Maybe a bit tangential, but like if you have an end of sentence going back into the model and the translation is happening after that, there would be a deterministic aspect to it where it would obviously have an SOS starting next. But if you have finished your prompt and then you have to start a sentence, so there would be a deterministic aspect where.
Yeah, but in general, you wouldn't be trying to do that. But yes, in that case, there would be. Yeah. But you're still going to have recurrence across sentences, right? So now what is the probability of any particular output sequence being drawn? The probability of any particular output sequence being drawn is the probability of the first word being chosen here times the probability of the second word being chosen here times the probability of the third word being chosen here, and so on. And so the probability of any particular output sequence being drawn is simply the product of the probabilities assigned to those words by the network, right? And so the objective of drawing over here is to pick the most likely word sequence. When I'm trying to convert an English sentence to German, the question you're asking is, what is the most likely German sentence, given that this was the English sentence? And so you really want to compute the sequence of symbols O such that the product of these probabilities is the largest. How can you do that? Yeah.
Here, when you're taking the probability, the Y1, O1, and Y2, O2, and stuff, is that just the probability of the occurrence of the word, or also the occurrence and the position?
So this is basically whatever is output by the network, right? So this is P of Y1 out here. This is P of Y2 in the second position.
And the position.
Yeah, obviously, right? Because the sequence, eh? Anyway, but this is the sequence of probabilities. How can you, so can you tell me, if I just pick the most likely word at each time, is that going to give me the most likely word sequence? No, right? So what would a solution be? So here's the problem, right? The greedy answer is I can just select the most probable word at each time, just do an argmax. This is not going to be good. And the reason this is not going to be good is, that if I choose, actually here's a nice visualization of it. Here I'm using an example of maybe a speech recognition problem. Speech goes in, a word sequence comes out. And let's say the first word I drew was the word he. And the second word, I just found out that when I looked at the probability distribution, the word knows, K-N-O-W-S, and the word knows both have very similar pronunciations. One of these things is this object on my face, and the other is a concept, that they both have very similar probabilities, but knows has a marginally higher probability. Knows has a probability 0.21 and knows has a probability 0.2099, right? If you just pick the most likely one, you're going to pick the thing on my face. But then he knows with an N is a very confusing sentence. What can follow? There's no obvious next word for he knows, right? So now if you go back and look at the sentence, you would find that it's very confused. All words are equally likely. It doesn't know what to do with it. On the other hand, if I had chosen the second most likely, the knows, you would find that this is a much more structured sentence, so some words pop out. So as a result, the probability of a three-length sequence of words becomes higher when I choose the knows as opposed to the knows, even though the knows was less probable, right? So clearly, if choosing do you mind shutting your laptop at the back? Thank you. Right? I don't mind you opening your laptop, just go outside. So anyway, so choosing the wrong word at any time, although it might be locally more probable, is going to make the whole thing less likely, right? And the problem is it's impossible to know a priori which word leads to the more promising future, because the issue might have been even earlier. Maybe in the very first word, the choices were he and thee. I just happened to choose he because, you know, he seems slightly more probable, but then thee nose with the nose on my face is going to end up with a much more probable future than he knows, right? So we need to be looking way out into the future to decide what the best thing to choose is, and we don't know the future. So what is the best, what is our option, solution? We are not going to, we know greedy is not good. And in general, making a poor choice at any time commits us to a poor future. So we need to have some other solution. Now, believe it or not, if you just drew randomly at each time, this turns out to be a pretty darn good solution. If you train your model properly, it's going to sort of pop up things in the right, with the right distributions. But, and sometimes it's going to be better than greedy, sometimes greedy is going to be better, but this is not a bad solution. But you really want to be doing something. So, you know, it could just be drawing a random sample there. But you want to be doing something smarter than that, because random sampling is obviously not guaranteed to give you the most likely word sequence. Yes, Saloni?
So will the random sampling work better when you have more data?
Random sampling is not going to guarantee you anything at all. Yes, I mean, if you have trained your model better, then your random sampling is probably going to do a pretty good job. But still, there's no guarantee that it's going to pick the most likely thing.
When you say better,
More likely in terms of probabilities, right? Right. So, yeah.
I'm confused about EOS. So when we're generating a sequence of words, how do we know?
If you randomly draw from the distribution and what comes out as an EOS, you're done. Right?
So do we like give a set of possible
No, EOS is an actual word in your vocabulary now.
Okay.
EOS is going to be part of the vocabulary. The probability table is going to include the EOS as a symbol.
So even EOS is going to have a probability.
At every time.
I see.
Right? You're adding EOS as a vocabulary entry. Yes, at that.
I didn't understand. Could you give an example, like how do you code out randomly sample from the output probability distribution?
What is the output of a probability distribution?
It will be the length of the word will be for each word.
It's going to be a category distribution, is it not? Do you know how to sample from a category distribution? How many of you know how to sample from a category distribution? How do you know? Do you know how to write code to roll a virtual dice? Raise your hands if you know how to. Come on. You do? How many of you have no idea how to sample from a discrete distribution? Raise your hands. Come on, guys. Are you raising your hands or are you not? Yes. So you don't know. Okay, he doesn't even know why he's raising his hand. That's meta. Okay. Anyway, how would you do it? Somebody who knows, how would you do it, Josh?
You take the probability that you have, or like you sample 0 to 1 with a random number generator. Take the first probability, subtract it, take it.
Yeah. So here's what I can do, right? I can take the interval 0 to 1 and segment it into the probabilities, right? So this is going to be P1. This is going to be P2. This is going to be P3. And I'm going to get n segments. The length of those n segments is going to be 1. Then I can randomly draw a number between 0 and 1. You can just use rand in your Python code. And that number is going to fall into some bucket. And that is the one you choose, because the probability of falling in that bucket is basically proportional to the length. You remember this now, right? All of you have done this. So you know how to sample that. Did that answer your question, Advait? Yeah. Anybody still in doubt? No. Okay. And so The number of eyes the owl has equals the number of questions on the page. Anyway, so your time's up. Does anybody from Zoom want to answer the first question?
True. True.
All right. Asmita, second one. True. Okay. Somebody from back there. Aishwarya, third one. True. Okay. All three eyes are true. Okay. You got the last one wrong. The procedure for randomly sampling was not in the slides, but you're right. I got it wrong. Thank you. You should have asked. You made me a liar. Okay, so we see that our choices can get us stuck, right? Our solution is to not choose. And so here's what I can do. I can run my encoder and get my final value. And then I make as many copies of my decoder as I have words. And every one of those copies, so for the first first word, of course, I just pass in the start of sequence symbol. So I'm fine. I'm going to get a probability distribution over all of the words. Then I'm going to choose every one of those words as input. And so now I have, if I have 100 words in my vocabulary, I have 100 copies of the decoder. Now, each of those 100 copies is in turn going to give me probabilities for 100 words. So at the next step, I make 100 more copies. And if I just follow this down, eventually I'm going to end up having evaluated every possible word sequence because I'm representing the words as a tree. Is this going to be feasible? No. So what would the solution be? Say it aloud. Beam search. How would I do the beam search? So what would the top three be dependent on? Okay. So here I have all of the words, he, the, whatever else, I, he, we. Each of those words has been assigned a probability at the previous time, right? I can just pick, say, the top two. Now, each of these two is going to expand out into 100 each. But then from here, I want to pick the top two. How do I choose the top two? It's going to be, I'm going to be multiplying the paths along the chain because I want the probability of the entire word sequence, right? So when I over here, when I chose he and thee, I already have the probability of he given everything in the past and thee given everything in the past. So for this block, I'm going to be multiplying the probability of he with the probabilities for each of these words. For this block, I'm going to be multiplying the probability of thee with each of these words. And that's going to give me the probability for all 200 paths from which I choose the two best. And then those can be expanded. So at each time, you already have a partial probability path. You're just going to be multiplying in the probability of the latest word into the partial probability path that you already have. And you're going to be choosing the largest based on the overall path, not locally, right? And I can keep doing this. When would I stop? I'm going to stop when I eventually, the current most likely overall path ends in an end of sentence marker. Okay, here's the thing. I don't stop as soon as I hit an EOS because it might be that the top path which runs into an EOS is not the most likely. The bottom path may be likelier. So in which case, I'm not going to be extending the top path anymore because the end of sentence has been hit. But the lower guy is going to continue to expand till eventually I get a sequence with an end of sentence marker where the overall path from the beginning to the end of sentence marker is the highest. And the nice thing with this process is that I can also draw this and use this to draw the second most likely sequence and so on. Now there's an issue with this. If I were picking the most likely outcome for a roll of dice, I just see the probabilities of all 6 outcomes and pick the most likely, right? In this case, what am I doing? I'm not actually evaluating all possible outcomes. I've got this tiny keyhole, which is my beam, and I'm scanning the world through this tiny keyhole to find the largest peak. So imagine you're standing in front of this giant landscape with lots and lots and lots of mountains, and I give you a pinhole camera with a really small hole. And you're going to have to find the highest peak. This is basically the problem that you're dealing with. You're going to be using all kinds of heuristics as you scan around, And maybe there's something like 50 kilometers high to the right, but you see this 2-kilometer high thing and say, yeah, I found it. Right? That's basically what you're going to be doing. Because that's this beam is the keyhole that you're looking at the world through. But it's the best thing we can do. So I have pseudocode for beam search. I will skip it and go straight to the point. Ten seconds, guys. Okay, my 10 seconds are up. Is the first one correct? Second? Thank you. So theoretically correct decoding requires you to evaluate the entire tree representing every possible word sequence. Beam search is looking through a keyhole. It is not correct. But it's an inadmissible heuristic, but it's what we've got. Yes, Isha?
I had a doubt with the beam search. So when K was equal to 2, why were we splitting at each node?
Pardon me?
Why are we splitting at each node? Like,
So here's what we did. We split over here, right? And we got 200, let's say. You chose the top 2, and then each of those split. But then when the first one hits an end of sequence, there's no more word. There are no more words after end of sequence. Your sentence ended. That's why. Yeah.
Would it make sense to reduce
No, not because you just used to. I mean, you could, but you're just being suboptimal, right? The larger K is, the more you're going to be evaluating stuff. So now after training the system, you must. So here is the thing. We are going to train systems using the maximum likelihood estimation procedure. What is the maximum likelihood estimation procedure? Anybody remember? Given a random variable and a model for the random variable, I'm going to go a few minutes over because it's tradition. Where is my chalk? I need to keep 5 minutes aside to search for my chalk in every class. So if I've got a collection of observations, and these came from, these are a set of, say, training samples from some probability distribution. If I'm trying to model the distribution, what I will do is to say, if they're all independent, I'm going to say P of xi semicolon theta. This is the joint probability of all of my data. Or alternately, if I look at the log probabilities, it's going to be log of P of xi semicolon theta. This is a function of just, since the x's are given, this is just a function of the parameter itself. And you learn the probability model this is how you actually learn your the parameters of your model. We're going to see maximum likelihood the estimation again in a few classes. But this is the general principle. The idea is that the world is very boring. So whatever you are seeing right now is very typical of the process that you're trying to model. So given the choice of all possible probability distributions, you're going to pick the one probability distribution for which this has the highest probability. You want to normalize whatever you have observed the most. And so using the world as a boring place principle, you get the maximum likelihood estimator where you're picking theta, which maximizes the probability of your data, right? And so going back here to our model, if I'm doing P of W1 semicolon theta times P of W2 given W1 semicolon theta and so on, what would the corresponding maximum likelihood estimator be? What does this mean? This literally means that you are feeding in the correct sequence of words at the decoder, right? And then you're feeding in the true sequence of words, and you're computing the probability of the true sequence of words also. And you're finding the network parameters that maximize this probability. Is that making sense to everybody? And so basically what you're going to do is you're going to be feeding in the actual sequence of words you want the network to output, because you're sort of you're literally just using this guy. You are trying to maximize the summation of I log of P of Wi given W0 to Wi minus 1 semicolon theta. This is the probability of W0 through Wk semicolon theta. And this term is what you're trying to maximize. And so if you choose your, basically, which is the same as saying, I'm going to be giving in the actual sequence of words, and then I'm going to be computing the probability of a word sequence. We saw how to do this earlier, right? From the output. And I'm going to choose the network parameter that maximizes this guy. And so you're just going to, you'd have a forward pass, you'd input the source and target sequences, and then you're going to compute the probability of the target sequence at the output, and you're just going to compute the KL divergence between the target between the probability distribution at the output and the target sequence, and just back propagate it, and you train your network. Now we're going to take a different perspective to this in the next class, but this is the maximum likelihood estimation procedure, and that's how this would work. Now, in terms of practical implementations, it turns out that instead of trying to choose the entire probability sequence and maximizing the loss over the entire sequence, researchers found that if you just randomly chose one word from the output for each sentence and used only the loss at that one word to update your network parameters, it worked more effectively. There was also, so the overall training is you'd be given several training instances. For each training instance, you compute the output of the network for X and D. Now here is the key piece. How is this differing from your standard training paradigm? In your standard training paradigm, you're just giving the X. You're not giving during the forward pass, you're not actually giving it the target output. You just give it the input, you get a target output, you compare the actual output to the target output and get the loss. Here you're actually giving it the input and the target output because we are performing the maximum likelihood estimator, which requires the word sequence, right? And then compute the divergence between some randomly selected words and backpropagate. It turns out, as somebody pointed out, that you're putting too much importance in that initial red box. And that initial red box is way at the end of the sentence, by which time you've forgotten everything about the beginning of the sentence. And it's also, when you generate sentences, it turns out it's much more important to be accurate at the initial portion of the sentence. Then you're more likely to get the trailing portion right. And so they like to flip the order of the input and present it in reverse order, and then generate the output. And that ends up working better, right? And the trick is still the same. So this would happen both during training and inference. So the overall training in this case is, you'll be given several training instances. You'd pass the input in reverse order. You get the final output right from the red box, pass it through the decoder, select some random samples from the output, and compute your loss. So many applications. This is a standard sequence-to-sequence model. And in the original paper, they showed how you can actually use this for things like machine translation, dialogue systems, and so on. There's an interesting observation that they got. The entire representation for the input sequence is being compressed into the vector at the red box. So does that really actually represent the sentence? They tried visualizing this and found these really cute pictures. When you project it down to 2 dimensions for visualization, here were 6 sentences. And each case, the red dot represents a 2-dimensional view of the blue dot represents a 2-dimensional view of the vector in the little red box. And so this is John admires Mary, John is in love with Mary, John respects Mary. This is Mary loves John, Mary admires John, Mary is in love with John, Mary respects John. Look at the arrangement, right? the patterns, the three relationships have the same pattern. The shift, John to Mary versus Mary to John is a constant shift for all three. It really captures the stuff. Or the one to the right. I was given a card by her in the garden. In the garden, she gave me a card. She gave me a card in the garden. And then the lower one is the same thing with subject and object reversed. And you can see that it actually captures the pattern. So what we are seeing is that little red box, the vector in the red box, does a fantastic job of capturing the semantics in the sentence, right? And they have some machine translation examples. I would love to read this, but then if I read this in French, you wouldn't even know it was French. So I'm not going to try. But I have been informed by those who know that these translations are really good, right? Here's one from a dialogue system. The machine, what is the error that you're running, please? And the human, this is humans responding, and the machine's responding to the human. I am seeing an error related to VPN. What is the error message that you're getting when connecting to the VPN using Network Connect? Connection refused or something like that. May I know the version of the Network Connect you're using? So you can see that it actually sounds like a real human being speaking, right? And this is just a very trivial sequence-to-sequence dialogue system, which is why you shouldn't be shocked at ChatGPT. This you could have done this 6 years ago, 8 years ago, right? So you can also use the same technique to generate captions for images. Once you separate things into an encoder and a decoder, the encoder could be working on anything. And so the first paper on captioning images, Show and Tell, by Oren Vinyals et al., they just replaced the encoder with a convolutional neural network that sort of analyzed an image and then used that to generate captions and train the network, and does a great job. So, given an image, process it with a CNN, and then just go through the entire sequence of words till you get a caption. And the training, the CNN is not going to be trained. You're just going to be training the language portion of the network. This is just a language generator, right? The only thing that changed between the standard language generator and this one, language model and this one, is the initial state. And we got some pretty nice captions. Anyway, I won't go through the captions. I'm going to stop right here. There is one key point here. In all of this, we are overloading that little poor guy in the highlighted circle. He's going to have to work really, really hard to represent a sentence. And if the sentence is long, his back is broken, right? So we need to do something better than that. And exactly how we do this is what we are going to see in the next class. Thank you.
I think that's